Welcome back, students. In the last lecture, we investigated some of the theory behind spectroscopy. To sum that up, since energy is quantized, molecules are only capable of absorbing certain wavelengths or energies of light. We saw that there were some selection rules that further limit the absorbable wavelengths, which simplifies the spectra further. Today, we're actually going to look at some spectra and get an idea of what happens when you shine light on molecules and induce their rotational and vibrational transitions. So the learning goals for today are going to be to compare and contrast the rotational and vibrational transitions and see the differences and similarities between them. And we also want to be able to interpret coupled rotation and vibration spectra. So we'll see some examples of these as we continue. To actually do absorption spectroscopy that we're going to be talking about, you need to shine light onto a sample. And the way that this is done in the instrument is that typically instruments have things called monochromators. And as the name implies, the mono being one and the chrome being color, they shine one color or wavelength of light at a time. And these individual wavelengths of light will go through your sample, and your sample will absorb some of them. And you can measure the absorption by Beer's law. You're familiar with this from Gen Chem. There's an extinction coefficient that talks about how well your sample absorbs. Then you have a concentration of your sample, and then this path length, which is standard throughout all of these instruments here. And the instrument will read the absorbance. As we've already seen in some of our labs, if we have too much sample, we'll absorb all of the light, and that's not going to give us an accurate measure of what's going on because we've absorbed all the light and we haven't actually probed how much stuff we have. And for this reason, spectroscopy is limited, and there's what's called a linear range in the instrument where Beer's law applies. Outside of that linear range at very dilute or very concentrated samples, you start to mess with this and you start to absorb too few photons or too many photons, and your accuracy is diminished. So you need to know the linear range of your instrument if you actually want to get accurate readings. I'll go into a little bit more detail about these instruments. Is that the monochromators, and they're limited to one wavelength, is not as accurate as you want. So most instruments have these settings, and we'll play with some of these in the future, called slit widths, and they determine how much light can actually get through because it's pretty hard to filter light by one wavelength. So for example, sometimes you might have a slit width of 2 nanometers, and that's going to allow your wavelength of light plus or minus 2 nanometers to get through to the sample. We can also try to think about how this technique is useful. And it turns out that bond vibrations, when we're talking about IR spectroscopy, are typically talking about vibrations. And these are largely independent of all other atoms in a molecule. So we can calculate the wavelength required to, or the wave number required to excite this transition, and we can get some delta E. And that is standard for each type of bond. So if you have a ketone in a simple molecule like acetone, or in a more complicated molecule like this, that carbonyl will absorb the same wavelength of light regardless of its context. And we are familiar with this from organic chemistry. We have these stretches that maybe we had to memorize or certainly had to be familiar with. And we would say, oh, we have a broad peak in the range of 3,500 inverse centimeters. That means we have an OH. We have a narrow peak around 1,700 inverse centimeters. We have a carbonyl, and so forth. So the fact that these bonds are independent of the rest of the molecule is going to help us make sense out of spectra for more complicated molecules, like you've done in organic chemistry. Now, unlike organic chemistry, we are not going to focus on small molecules here. Our focus will be on diatomic molecules, and if we're feeling lucky, we'll even move on to triatomic molecules. But we're going to see that there's a lot more information that you can get out of studying simpler molecules that kind of is masked by the more complicated molecules like you would have done in organic chemistry. So let's look at some spectra for two molecules. We'll look at methane, CH4, and carbon monoxide. One of the first things we want to address is going to be how can these molecules actually vibrate? So these molecules will have 9 rotational or vibrational degrees of freedom for methane and only 1 for carbon monoxide. How did I get that number? All molecules have 3 times n, where n is the number of molecules degrees of freedom. And this stems from each atom in the molecule being able to move in any of the 3 directions. So carbon monoxide has 6 degrees of freedom and methane has 15 degrees of freedom. Now, if we want to think about specifically vibrational degrees of freedom, essentially our vibrational degrees of freedom are everything that is not a rotation or a translation. So molecules can translate in 3 dimensions, and polyatomic molecules can move in, or not necessarily polyatomic, but nonlinear molecules can move or rotate in 3 dimensions, whereas linear molecules can rotate in 2 dimensions. So for that reason, nonlinear molecules have 3n minus 6 vibrational degrees of freedom. So to get 9, we take 15 for methane minus 6 equals 9, whereas linear molecules have 3n minus only 5. So 6 minus 5 is 1. So carbon monoxide has 1 vibrational degree of freedom and methane has 9. And so what we might expect to see with this is 1 nice peak for carbon monoxide and 9 peaks for methane. So we'll go ahead and look, and we don't see anything like we expect. So for methane, we do see sharp peaks, and we see this kind of schmutz here on the side. And for carbon monoxide, we don't see a peak at all, and rather we see this very broad stretch with a weird divot in the middle coming out of it. And for the rest of the lecture, we're going to try to make sense of these strange observations. So some of the things we can say what's going on here, we'll start with methane. So why do we only see 2 peaks instead of 9? It turns out that some of the peaks for methane or some of the vibrational modes for methane are symmetrical. And so if we have a symmetrical mode, we're not going to be able to see that, right? Because remember, for something to be IR active, it has to have a non-zero dynamic dipole moment. So if we have a symmetrical mode, we're not going to be able to see that. So here's an example of a symmetric stretch here for something like carbon dioxide. So some of the modes are not visible because they are symmetric. And others of the modes are energetically degenerate, so they will overlap with each other and appear in the same wavelength. But so we end up with 2, and that doesn't explain why we have this schmutz on the side, and also what the heck is going on with our carbon monoxide. And in the rest of the lecture, again, we're going to explore this. At the end of the semester, we're actually going to talk about group theory. And that will help explain some of these things about why we don't see some stretches and why some of our stretches are degenerate. And at the end of the lecture today, we'll move into rotations, and that will explain the schmutz here and also the strangeness of our carbon monoxide very broad peak. So for rotational spectroscopy, it's going to be the same kind of thing as we talked about for vibrational spectroscopy. And we need, again, to have this non-zero transition dipole moment. We'll define the transition dipole moment here as mu times cosine of theta. We're not going to go into this too much, but it turns out that for rotating molecules, we also have a selection rule. And for example, if we started at the ground state and went to the first excited state, we'd have a non-zero transition dipole moment. But if we went to the second excited state, we would end up having a 0 transition dipole moment. And again, I don't want to go into this in too much detail. It's very similar to the process for vibration, but the math is more cumbersome. So what we end up with is a transition where instead of having +1 like we have for vibration, we have plus or minus 1, and these are the transitions that are allowed. And technically for vibration, I think we would have a -1 transition be allowed too, but if we're all starting in the ground state, there's no minus to go to. We'll see, and we've seen before in the homework, that this is not the case for rotation. So if we calculate our rotational energy levels, we have this B constant. I introduced this last time. You can see here it's a pooling of many other constants, including the reduced mass and the equilibrium bond length. That's going to be independent or dependent on the types of molecule. And we can end up with the following. So if we try to take delta E in the forward direction, so going from, say, 1 to 2, we end up with an energy that's equal to 2 hCb of J plus 1. And if we went in the reverse direction, say from 1 to 0, we actually get a different delta E that's negative 2 hCb times J. And we can see that these energy levels are not equally spaced. But as I mentioned in class before, if we were to take the difference in these energy levels, so here going from 0 to 1, we have 2, from 1 to 2, 4, 2 to 3, 6. The difference between all of these energy levels is 2. And what that means is that they are actually equally spaced. So if we were to excite rotational energy levels, we would see a bunch of peaks based on where the starting point of these molecules are, which we can see is not all at the ground state. And the height of these peaks is going to be proportional to how many molecules begin in that state. So here we could see an example of a molecule. Here would be the 0 to 1 peak, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. And we see here that the largest peak is the 7 to 8, which indicates that most of the molecules are beginning in the J equals 7 state. And then it decreases as well as we get less populated at the higher energy levels. So I've been hinting, and we've done some calculations before to show that a lot of rotational energy levels are accessed. And we can look at some examples here for HD, so hydrogen molecule with one of the hydrogens being deuterium or carbon monoxide. And what we can see is that at most temperatures, a lot of states are accessed. And of course, this is molecule dependent. So the larger the atoms in the molecule, the more likely we are to be in higher excited states. So for something like hydrogen deuterium here, not very many states are accessed at room temperature. We have a significant population up till about J equals 4. For carbon monoxide, on the other hand, with bigger molecules and a weaker bond, we end up having all the way up to about J equals 25 active. And of course, at higher temperatures, both of these will be shifted to higher numbers of states active. And we can do some calculations, and you've done these kind of calculations to show that this is the case, that all molecules have a significant amount of rotational levels accessed. And that's because the spacing between those levels is small compared to the thermal energy, so they can excite easily between them. We can also note here that for carbon monoxide, we actually end up having a spectrum that looks fairly continuous, right? So our HD over here looks pretty discontinuous. You can see it's kind of jarring here, the transitions. But for carbon monoxide, we see a pretty continuous looking spectrum. So the next thing we want to be able to do is try to figure out what's going to happen if we actually were to take one of these molecules into the lab and measure its rotational and vibrational spectra. So let's compare the energy levels of rotation and vibration. And what we want to do is compare the magnitude of these levels. So the vibrational energy is equal to hc nu, where the rotational energy is equal to hcb times jj plus 1. So this gives us an equation here that relates our constant b to a constant nu. And what we can find out is that for different molecules, these are relatively different. So what I have here is indicating that for hydrogen, we can fit about 8 rotational levels inside of its vibrational level based on its constants b and nu. For carbon monoxide, we can fit about 16 rotational levels inside of its vibrational level. And for something like hydrochloric acid, we can fit 33 rotational levels in there. So what does that mean? What does that look like? Well, if we consider a molecule like a harmonic oscillator, this is shown here for hydrogen, we can expect that in the transition from the ground vibrational state to the excited vibrational state, there's also rotational transitions that are happening in and among the vibrational transitions. And when we make these transitions, we actually have to account for the selection rules for both of these transitions. So for the ground state, what we would have, right, is we're basically always starting in the vibrational ground state, but that's not true for the rotational state. So for hydrogen, we could start in the vibrational ground state and the rotational ground state, but we could also be in the first, second, third, or fourth vibrational state. Now, I'm considering hydrogen here just because the numbers are small. Remember that hydrogen is homonuclear diatomic, so it's actually not IR active. Then we'll move in and say, well, what transitions are we actually allowed to observe? And this is going to be according to our selection rule. So we're allowed to have delta n is equal to +1 and delta j is equal to plus or minus 1. So what transitions does this give us? Well, if we start in 0, 0, we can increase only both of these by 1, and we'll have a peak that corresponds to 1, 1, the transition from not just the ground vibrational state, but also to the ground, or to the excited vibrational and rotational state. So that would be from right here in this black line up here to this first red line. If we don't start at the black line, we start in this first line according to the first rotational state, we could either transition up to -1 rotational state, or we could go up until 2. And so there's two options there to having an n+1 and then a j+1 or a j-1. So we see that there are, for this simple case for hydrogen, there would be 9 possible peaks that we see. And of course, for more complicated molecules that have more, or not necessarily more complicated, but for larger molecules that have more rotational states access, there's going to be more peaks that we see. But note, what we don't observe is that there is not an allowed transition from n equals 0 to n equals 1. That transition is not allowed because we have to have a j transition as well. So this tells us why we saw this big divot in our carbon monoxide spectrum here. It's because that divot was corresponding to a j equals 0 state, and that is not allowed. And the rest of those big broad peaks in the side were all of these various rotational transitions of j+1 on the right side and then j-1 on the left side. So if we look at some actual spectra, we can see what's happening here. This is for HCl, I believe. And we can see that we have, again, what's called the R branch on the right side and the P branch on the left side. And the designations here is R branch is going from going up 1J and the P branch is going down 1J. And we don't see anything in the middle here. And if you were to put this on something like our carbon monoxide from before with pretty high resolution, what we'd end up seeing is something like this. And you can see how this would end up looking as a big broad peak with a big divot in the middle here, where again, what we see, the magnitude of the heights of these peaks correspond to how likely those states are to being accessed. So you might be wondering, well, we had that methane, and that did have a really strong peak in the center. And that is essentially because methane is a polyatomic molecule. So these polyatomic molecules have different kinds of transitions, and we'll look more at that in lab in the future when we do IR spectra of polyatomic molecules. So to conclude here for this chapter, our spectroscopy is something that where we have a different quanta of energy being absorbed. And this only makes sense if energy is quantized. Otherwise, you'd get continuous absorption spectra. We can't uncouple rotational and vibrational energy levels. So if we excite a vibrational transition, the rotational transitions are coming along with it. And that makes the spectra not nice and clean peaks, but rather having these many different peaks. If those peaks are wide enough apart, we actually can resolve them. And in some cases, we'll see they become unresolvable as those energy levels for rotation get close together. At room temperature, only the ground vibrational state is active, but many rotational states are possible. And that again gives rise to the spectra that we see. Our selection rules limit the transitions that we're allowed to see, which simplify our spectra. And some key things to note here as well is that these bond vibrations only depend on the atoms in the bond, which will lead us to things like chromophores in the future. So chromophores are going to be specific bonds or groups of molecules or atoms in a molecule that absorb special kinds of light. So we already saw this with UV vis spectroscopy, is that conjugated double bonds act as a chromophore and absorb wavelengths of light that are different than the rest of the stuff in the molecule. And that helps get identifications on these molecules. Before we go, I want to briefly mention Raman spectroscopy. We'll see this in lab. Raman spectroscopy is another type of spectroscopy that probes vibrational transitions. However, it does so in a different way that has its own different kinds of selection rules. So the way Raman spectroscopy works is you ram high energy photons into molecules, and these are typically things like red light. So photons with red light, which is much higher in energy than infrared light. And when this happens, some of the energy ends up being, or can end up being, transferred to the molecules. And that causes them to vibrate. So with this, we can actually observe vibrational modes for molecules that are IR inactive, such as some symmetric stretches. And we'll do some Raman spectroscopy in lab, and I'm happy to take questions about this in class if you want to ask. And the book goes through this technique in some detail as well. And with that, I'll let you go, and I'll see you guys in class to talk about spectroscopy.